Let's take a look at how rendering and render prims work in USD. We'll cover the various render prims, converting a pre-Houdini 21 render pass setup to use render pass prims, rendering with the USD Render ROP, then finally, my rendering workflow with Deadline. Broadly speaking, in CG, we have a scene file containing our 3D data, then we might have various subsets of that scene we want to render, usually called takes or render layers. We send each take to a renderer with settings to specify things like image quality. The renderer then calculates the desired image, which can contain multiple data planes or AOVs. USD is no different, but as usual, it has its own names for these concepts. The AOVs are called render vars. One or more render vars make up a render product. This is the file output by the renderer. Render products are produced by render settings, things like sampling quality and ray depths, and those render settings are used to render a render pass, which is a particular subset or state of the stage. Now, this isn't just a new set of names to remember. There are two really powerful ideas that make this system so useful. First, these are all primitives, so they exist as objects in our scene graph tree. This means that you can store and reference libraries of render setups in the same way you store geometry. And since your render settings aren't locked into app-specific project files, they can be passed between applications. The second powerful idea is that each of these prims can selectively override information. For example, render vars can override compression settings set by render products, which can override the camera and resolution set by the render settings. This allows for the construction of fairly elaborate render setups that are simple to kick off, like rendering a high-res multi-camera scene with all the render vars alongside a low-res beauty output from a reference camera. Let's look at how to implement these in practice using Karma in Houdini 21. The Karma render settings node gives you everything you need to get a render going. With it, you can set up all of your render settings and AOVs in one place. In the scene graph tree, you can see that it's created all of our render prims for us. We have a render settings, which is pointed to a render product, which is pointing to the beauty render var. This is really convenient, but let's rebuild it from scratch to fully understand how it all works. First, we need the render var prim. As you can see, this defines a number of important properties for the AOV, things like name, format, and which rays to include. There are a few nodes for creating render vars: Karma standard render vars, additional render vars, and render var. There's also a Karma specific node to help with creating cryptomatte render vars, but we'll ignore that for now. Each of these nodes has their own use cases, but for the most part you'll only use the first two. That said, let's go through them one by one and make our beauty render var with each. Starting at the highest level with the Karma standard render vars node. This node makes it easy to add a bunch of the usual AOVs you'd want for comp. By default, it's creating a bunch of extra vars we don't want right now, so we'll turn them off by unchecking them in the parameters pane. Done. We have our beauty var. Next, we have the additional render vars node. Here, we can add vars using the multi-palm. Click the dropdown next to name, and we get a handy list of presets for pretty much all the AOVs you might want. We just want the beauty, so I'll click that. This conveniently populates most of the settings for us. We have the name, which I'll change to beauty for consistency. Data type and format determine the number and precision of channels in the render and output respectively. And we'll want to turn on multi-sample, since this isn't a data pass. The source type and source name here means that this render var is a light path expression, which is a way of specifying which rays to include in the AOV. LPEs are a deep topic in their own right, so I won't get into it here beyond a quick explanation of what this means. C means camera, dot means anything, and the star means any number of times. L and O are for lights and emissive objects respectively, and they're in square brackets, which means either or. So this LPE is saying, include all rays that start from the camera and end at a light or emissive object, regardless of what they hit while bouncing around in between. I might cover LPEs properly in future, but hopefully just from this you can see how useful they could be in crafting hyper-specific AOVs to suit your needs. Lastly, at the lowest level, we have the render var node, which, as the name suggests, will create a single render var prim. We'll name it beauty. We'll change the data type to color 4F so we get alpha. Next, we need to set the source type. Raw is used for AOVs defined in materials. Primvar is for primvar values, which are basically what USD calls attributes. Intrinsic is just a placeholder in case USD introduces a set of standardized render-agnostic render vars, which would be awesome, but it hasn't happened yet, so we can ignore it. LPE, as we've covered, is for light path expressions, which is what we want for our beauty render. Then for source name, we'll put in the LPE we walked through earlier. C for camera, dot star for all bounces, LO in square brackets for ending on lights or emissive objects. Next, in the Karma tab, we'll set the pixel filter. We skipped over this in the previous nodes because it was set by default, but this tells the renderer how to combine pixel samples. Click the dropdown and select average samples. Then finally in the Husk tab, we can set the format to color 4H, which is 16-bit RGBA, and optionally change the name to C, which is the default beauty channel name in Houdini. All done. Now we've implemented a beauty render var with 4 different nodes. This is of course completely redundant, but knowing how the lower level pieces work can give you a much greater understanding of how everything works at a higher level. I also hope this helps highlight that in USD, AOVs aren't special settings buried in a hidden render settings window of your app-specific scene file. They're just primitives with attribute values attached, so you can create, edit, and share them like with any other USD data. With all that said, we can delete these extra setups and move on to creating the render product. Unlike with render vars, there are only two nodes for creating render products: the aptly named render product and Karma render products, the latter of which is simply a handy wrapper for creating multiple render products at once, so I'll skip that one here. By default, the product will be named after the node name, so let's call it render product to match the default setup. Under ordered render vars, we can point to the vars we want the product to output. In our case, it's just the beauty. You can also use pattern matching to grab multiple vars at once, so vars/star will assign to every render var under the vars scope. Next, we'll set the product name, which is the output file path. The usual default is $hip/render/hipname.os.f4.exr. Since we've included the frame number, this makes the node time varying, so I'll set it to sample frame range to cache the values. You can check the paths in the scene graph tree by selecting the product name property and looking at the time samples in the right pane. Product type you can ignore. Raster means that the product will output 2D images, which is the only supported setting at the moment. The rest of the parameters here we'll set on the render settings, but just note that you can override them per product. Under the Karma tab, you have deep settings, though if you're watching this, then I doubt you're rendering deep images. Then under Husk, we have color space and EXR compression, which can also be overridden by each render var. And that's our render product done. Next, we can put down a render settings LOP to add to our render settings prim. First, we have ordered products, where we'll want to point it to our render product. For included purposes, I'll add the render purpose, though it's not strictly necessary as Husk will include that by default. Material binding purposes and rendering color space we can leave as is. Then here we can set the camera and resolution, and disable motion blur and/or depth of field. Data window lets you set crops or overscan, and pixel aspect ratio is here if you need to render anamorphic or some other exotic pixel aspect. You'll probably never need to do that, but non-square pixel aspect ratios have been surprisingly handy for me in solving some niche rendering challenges over the years. Moving on to the Karma tab, we have all the usual render settings. Note that the CPU and XPU render settings are all mixed in together, so it's a good idea to read the docs to learn which settings are CPU or XPU specific. For XPU, the main ones you want to set are path trace samples for the overall render quality and diffuse limit for global illumination. Now there's one last thing to do that the Karma render settings node normally handles for you. Under advanced, there's a parameter called set as default render settings prim. This adds this render settings prim path metadata to the layer, which lets the renderers know which render settings prim to use by default. We can add this ourselves with a configure layer LOP. Toggle on render settings and point it to our render settings prim. Done. This isn't strictly necessary here, as Husk will automatically look for a render settings prim at that path anyway, but it's probably a good idea to be explicit, especially if you end up adding more render settings prims later on. Now that's everything you need to get a render going. Let's test it out on a test scene. I'll go with the Cornell box. Then set the camera on the render settings, and start a Karma XPU render in the viewport. If we want to add more AOVs, we can simply add another render var. I'll use the additional render vars node, and add normals. Now we see our normal AOV in the list here. It was added automatically because on the render product, we're pulling in all of the render vars. You can ignore the depth, prim ID, and instance ID AOVs here. They're auto-generated in the viewport and won't be included in the rendered file. Speaking of which, we can render to disk by putting down a USD Render ROP, setting the engine, and hitting render. If you want to see the render progress, then turn on Mplay Monitor. Now for the final piece to the render prims puzzle, let's add a render pass by putting down a render pass node. These four sets of options let you determine which objects to include, matte, phantom, and prune at render time. Let's test them out. To render with the pass, in the viewport, click the perspective button, and under render pass, select your pass. On the render ROP, you can set it using the render pass parameter. The pass looks the same right now, so let's fiddle with the pass collections. The renderable objects collection lets us explicitly decide which prims to include in the render. The default slash will include everything. If I set it to just the light and box prim, the boxes disappear. Matte objects will render as 0 alpha. Any prims not in the camera visible objects collection will be phantoms, or invisible to primary rays. And pruned objects are prims to remove from the scene. This is similar to not including the prims in the renderable objects collection, but will actively prune the prims rather than simply setting them to not render, which is likely to be more efficient for heavy geo. With all of these, you can expand to get more options. USD path expression determines whether to evaluate path expressions upfront or later. For example, if we prune world contents *_box, this pass will prune everything under the contents prim that ends in _box. Toggling the USD path expression gives the same result right now, but what if we added another box later? The extra box is only pruned when the USD path expression is turned on. You can see in the scene graph tree that with it off, the star is evaluated immediately to include only the original boxes explicitly. Whereas with it on, we instead store the expression to be evaluated later. This is a little slower, but it allows you to define the collection dynamically to include prims that may not be in the scene yet. We also have exclusions, but they can be a bit finicky. For render visibility and camera visibility, this expansion rule is on by default, which means that prim paths in the include pattern also apply to children. So the default slash here propagates through to include all children, and then you can exclude just the ones you want. So with the default excludes, I can choose to not render the tall box and phantom the short one. In the matte objects collection, this expansion is off by default. So if I include the parent of the boxes, nothing happens, as only the parent XForm is being set to matte, not the boxes themselves. Setting the expansion to expand prims fixes this. Then we can exclude specific children as well. Lastly, with the prune collection, we can't seem to exclude the child of a pruned prim at all. For example, if we prune the parent of the boxes and then exclude the short box, you might expect that the short box would be visible, but it's not. Since we're including the contents prim, even if we exclude a child, it won't render because contents is being pruned. Changing the expansion rule won't solve this either. The solution is to change the include to contents/star to only include the children of contents, and then we can selectively exclude them. Then down here, you can set metadata. Unless you're in a studio pipeline, you can ignore these, as they don't actually do anything by themselves. That said, I would recommend at least setting the render source. This lets you point to the render settings prim that should be used to render this pass. I'll point it to our render settings prim for this example. It can serve as a useful note to remind you which passes should use which settings, or you can reference it with Python, but we'll get to that later. For now, let's look at reorganizing an old scene file to make use of render passes. Here's the branching render pass setup from LOPs for solo artists. On one branch, we have a geometry pass with just the geo. And on the other, we have an effects pass with the particles and a holdout AOV. Let's start with the geometry pass. We'll keep the base global render setup as is, but duplicate the product and render settings for the new pass. Set the duplicate node to source primitives are first duplicates, as we don't want to deactivate the originals. And for the name, I'll replace this @copy suffix with the pass name. The new prims are blue because by default, the duplicate will create instanceable references to the original prims, which is useful for our setup because it means we can make global changes to all of our render settings prims in one place. Our scopes have turned into XForms though, so under the primitive definition, set parent primitive type to none to leave the hierarchy untouched. Great. Now this render product edit just needs to be pointed to the render product geometry prim, and it'll set the product name as before. And I'll set it to sample frame range to get rid of the time dependency. Then with a render settings edit, we can point the geometry render settings to the geometry render product. Now we can add the render pass. I'll call it pass_geometry. And on this branch, we're pruning the shot effects prim. So we can delete the prune node and instead put shot effects into the prune objects collection of the geometry pass. Now I'll just set the render source to the settings for this pass and we're done. In the viewport, if we render with the geometry pass, the particles disappear. Now let's look at the effects branch. We'll copy the duplicate node and change the name to effects instead of geometry. Point the render product edit to the effects product, which will set the output path and AOVs. And same as before, I'll set it to sample frame range to remove the time dependency. Now I'll point this render settings edit to the effects settings and point it to the effects product. Then I'll move it below the product edit so it matches the node order on the other branch. Now to add the render pass. I'll call it pass_effects. And for this branch, we prune the lights and matte shot geometry. So I'll delete these nodes and add lights to the prune collection and shot geometry to the matte collection. Next, I'll set the source to the effects settings and do a test render. There are two things to fix here. First, the geometry isn't being matted. This is one of those gotchas we covered earlier. The render geometry settings node expands prims by default, but the matte collection doesn't. So under the matte collection, turn on expand primitives. If the viewport gets stuck, you can toggle the render pass on and off to give it a kick. Now in the AOVs, we don't have the holdout var. That's because changing the render pass won't automatically change the render settings. So under perspective render settings, we need to select the effects render settings. And now we can see the holdout AOV. Now we still have two branches, so let's inline them both together, and we can delete the extra render node. We can now switch between the passes and settings in the viewport. And we can save the whole scene as a single USD file that contains all the information for rendering the scene and both passes. I'll cover my preferred rendering method next, but let's look at using the render ROP first. We can set the pass here with this dropdown. I'll set it to effects. We could manually specify the matching render settings, but where's the fun in that? We've already told the pass which render settings to use via the render source attribute. So let's use a little bit of Python to read that and set it automatically. On the render settings parameter, right-click and select expression, edit expression, and set the language to Python. Cool, now we can do some Python magic. Here's the script I use. First, we get the render pass path from the pass parameter. Then, we get the USD stage, and from that, get the pass prim using the path. Next, we get the pass prim and query the render sources, and return them as a space-separated list. Hit apply, and now we can switch passes, and the settings will update automatically. And so you never need to remember this script again. Right-click on the parameter, go to Recipes, and Save Parameter Preset. Call it something like Settings from Pass, and hit Save. Now, when you drop down a render ROP, you can add the expression from the recipe. Let's test the passes by rendering to disk. First, the geometry pass. Done. And then the effects pass. Done. Here we have the rendered frames, the geometry pass, and the effects pass, with the hold.AOV. By the way, if you haven't been using DJV for checking renders, you should give it a go. It's the best. Darby has just released a new version this year with a whole new backend, and it's incredible. Get it on his GitHub here. And while we're on GitHub, here's where you can grab the plugin that I use for rendering with Deadline. I covered this briefly in LOPs for solo artists, but let's look at how that workflow has changed since Houdini 21. First, I'll save to USD. Only one USD file is needed now, instead of one per pass. Then, in the Deadline monitor, I launched the Husk standalone submitter and point it to the USD render. I've completely rewritten this submitter since last time, and one of the main reasons for that was to improve the render pass workflow. On the render ROP, you'll note that you can select multiple render settings to render at once. You can even use patterns. But you can't do that with passes, which is a little disappointing. So I made my Deadline submitter implement a similar logic for passes and render settings. Simply putting star for pass will submit all passes as separate render jobs, each with the render settings prim specified by the render source attribute. It'll also automatically set the frame range from the USD files. To avoid having to submit from the monitor all the time, I've added the submission script to the context menu in File Explorer. And this is pretty niche, but if you like shell scripts, here's what I've set up to make submitting scenes faster when I'm jumping around multiple shots. I can see a quick preview of the files, and then send the ones I want to render. Alternatively, I can just grab any recent ones and submit those. This is super nerdy and unnecessary, but I find it fun to play with. And that pretty much wraps up everything I can tell you about using USD render prims and how you can set them up in Houdini. You can certainly just use Karma render settings nodes and ignore most of what I've covered here, but at least you should now have an understanding of how it's all working behind the scenes, so you can tweak your setups to work exactly how you want. There were so many great new additions in Houdini 21, but I really wanted to cover render passes because they're so useful and I've been looking forward to their inclusion for ages. They're a bit cumbersome to use though, so without a bit of guidance, I could see a lot of artists missing out on such a great feature. Hopefully I've succeeded in helping at least some of you get into using render passes. There was a lot to cover despite the relatively narrow scope of focusing on render prims. I had to cut out a whole section on schemas and values that I might revisit in future one day. For now though, best of luck rendering your scenes.